All right, can we quiet it down, please, so I can dive right in? So yesterday, wasn't yesterday just actually a lot of vocab, basically? Now today we're actually going to get to dive in and see how do we start setting up these experiments. Just like with sampling methods, we're going to start with a very generic one, and then we're going to branch off into some more interesting ones in the next couple days. Okay, so the remedy for confounding, remember confounding yesterday was kind of this background variable that could be masking the effect of your explanatory variable, right? So the way that we remedy that is by performing a comparative experiment in which some units receive one treatment and similar units receive another. Most well-designed experiments compare two or more treatments. Comparison isn't enough though, right? Comparison alone, if the treatments are given to a group that differ greatly, bias will be or will result. The way to get rid of bias is random assignment. If we take our subjects, we need to randomly assign them to a treatment group. And again, in doing so, the goal is to make groups as similar as possible so we can actually make those comparisons. When we need to randomize, again, what's the easiest way to do random assignment? A hat, right? Our hat trick. Put names in a hat, draw them out, and then you can start assigning them to those treatment groups. So the first one today, the only one today actually, we call a completely randomized design. Okay, so if you're thinking of how does this relate to sampling methods, this would basically be like an SRS, a simple random sample. Okay, again, don't mess up that vocab, but just saying if you could relate this to a sampling procedure, this would be kind of that simple random sample, right? Everything's perfectly random. Now, one thing that is important though is usually we're going to want some sort of control group, okay? Now, a control group is a group that doesn't actually receive a meaningful treatment, okay? We kind of leave them alone, we leave them be to see what would happen if we did nothing, okay? Because if we just give everybody a treatment, is that going to be an authentic result if we can't compare to what would have just naturally happened anyway? No. Okay. So again, usually control groups are going to be important in this process, right? We need some sort of comparison to make. So this is just a little visual of how this process flows, right? So we have our experimental units, or again, if they're people, we call them subjects. We randomly assign them to a group. Again, that random assignment is critical because it creates groups as similar as possible so we can make those good comparisons. Each one gets a treatment. Then in the end, we compare the results based on the treatment. So we compare what happened based on the treatment they received or lack of treatment if we're talking about the control group. Okay. Now, on the AP exam, this unfortunately isn't enough to answer a question. This is just a good mental map that you're going to see me do, okay? This is a good way you can map out your thoughts, and then you can write your little paragraph underneath it describing what you're really doing, okay? So you don't have to show me this. I just like it, and I think it helps some kids just kind of plan out their thought process. What am I doing? How am I breaking these up, okay? So let's just dive into our first example so we can start talking about how this is going to go. So this is actually a true FRQ that was given back in 2009. Before beginning a unit on frog anatomy, a 7th grade biology teacher gives each of 24 students in the class a pretest to assess their knowledge of frog anatomy. The teacher wants to compare the effectiveness of an instructional program in which students physically dissect frogs with the effectiveness of a different program in which students use computer software that only simulates the dissection of a frog. After completing one of the two programs, students will be given a post-test to assess their knowledge of frog anatomy. The teacher will then analyze the changes in the test score. Score on post-test minus the score on the pre-test to see each student's growth, okay? So we want to talk about describing a method for assigning those 24 students to two groups of equal size that allows for statistically valid comparison of the two instructional programs. All right, so that is just kind of a long-winded way of saying how would we set this up? How would we actually do this, okay? So we have, again, just to show you how this mental map would work, we have 24 subjects, right? So we're starting with 24 subjects. Now, it's usually assumed you want equal size groups. Didn't they specifically tell you that this time? Right? So here's kind of the only math you're going to see this chapter. Can you divide by 2? How many people in each group? 12. So we're going to split these kiddos up, right? Split them up. I usually put an RA here to show this is where I'm going to randomly assign them to a group. And we'll come back to that in just a second. So there's 12 kids that are going to be in group 1, 12 kids that are going to be in group 2, all right? And then each one receives a treatment, okay? So this one, maybe we're going to say this is actual dissection. And then what was the other group? What's the treatment associated with that? Computer simulation. All right, and then in the end, we always have to say what we're going to do. So here, what are we going to compare between these two groups? Yes, we're going to compare student growth, right? Post-test minus pre-test. So again, you don't have to do this, but I think it's just a nice mental map, right? We know where we're headed. We know what we need to do. And then you guys already told me earlier, you even know what we're going to do here. Okay, what's the easiest way to randomly assign? Put it in a hat. Mix it well, yeah. So we're going to put all 24 subjects' names into the hat, okay? Mix it well. I'm going to pull out 12. What do we want to do with those first 12? Okay, we'll put them in the actual dissection group, all right? So the 12 that I select, I'm going to designate that they're going to be in the actual dissection program. Now, just saying that isn't enough, though. You have to address everyone. So you actually have to also specify what's going to happen to the names I didn't pick. What's going to happen to the 12 that are still in the hat? What am I doing with that group? Yeah, they're going to do the computer simulation, okay? You have to specifically address every group, okay? Does that make sense? So even though it seems obvious the remaining 12 are going to do the computer simulation, you do have to specifically say that, okay? So the 12 that I draw are getting actual dissection. 12 that I did not draw are going to be in the simulation group. Again, after this, we're going to compare the student growth. Oh, I've done worse to you. Come on. All right. Suppose the teacher decided to allow the students in the class to select which instructional program on frog anatomy, dissection, or computer simulation they prefer to take. The 11 students choose actual dissection and 13 choose a computer simulation. How might that self-selection process jeopardize a statistically valid comparison of the changes in the test scores, post-test minus pretest, for the two instructional programs? Provide a specific example to support your answer. All right. So we're talking about it'd be poor of us to allow them to choose which program to do, okay? And this actually goes really well with that idea of confounding that we talked about yesterday. Their choice is going to confound with the effects of the program itself, okay? Something we didn't control for. Um, Again, it might be difficult to brainstorm off the top of your heads. Um, but here we're talking about preference. They're going to do what they already like, okay? Now, let's think about this, okay? Someone who's naturally good at biology and really, really likes biology, which one might they be more interested in naturally? The actual dissection, right? The real thing. Again, maybe not always, but is it plausible to believe that a student that is good at biology, that really likes biology, they are probably intrigued by the process of dissection. Now, think of it this way. Didn't I say that maybe they were already good at biology and that's why they're interested in it? So if they're already good at biology, what's going to happen with their growth if they're already good at it? What? It's not going to be as much, right? If you take a collection of people that are already good at something and you try to teach it to them, well, again, they're not going to have much growth as maybe this computer simulation group. If those are the kids that don't have that strong background, don't they have quite a bit more growth to have naturally? Is everybody following me on that? Does that kind of make sense? So again, that would be a great example of confounding. Okay, their choice is going to limit the growth for, or could limit that growth of the actual dissection group. If they're already good at it, they're already interested in it, they're not going to have as much growth to have as that other group. Okay. Now, I know this is a lot. Feel free to paraphrase. Okay. Feel free to write whatever makes sense to you. Okay. You don't have to write exactly what I did. Write something that makes sense to you, but that hits those key points that I mentioned. Okay, because I realize that is a lot. You also realize I tend to be more thorough than I expect you guys to be just to model good answers. What? Why? I get really gross. Like, I look like a disgusting lumberjack if I stop shaving. Like, I did it once and never again. Wait, are you actually doing it though? Oh boy. Can you grow facial hair? Sometimes. All right. All right. So now, let's talk about what could go wrong, okay? So that's what a good experimental setup would look like. But there's a couple of things we also have to watch for, okay? So two more vocabulary terms, which I think are pretty self-explanatory for most people. First of all, double blind. So sometimes it's appropriate to create a double blind experiment, all right? Now, what that means is that the individual doesn't know which treatment they're receiving, and the researcher that interacts with them also doesn't know which treatment they're receiving. And the reason we would do that is so the person interacting with them, just in that interaction, can't lead them to give specific responses as to how the treatment is going. Okay, so someone in the background obviously knows, but just I'm saying the person directly interacting with the subject actually is not aware which one they're receiving. So really quickly, let's talk about why would this scenario, it would be impossible to make double blind. It just wouldn't make sense. Why would it not make sense to make this a double blind experiment? Why can't we do it? Yeah, is it possible for the student to not know if they're dissecting versus on a computer? Is that possible to hide from them their method of learning? So yeah, so in this instance, it doesn't make sense to try to make a double blind because you literally can't. So that isn't something you have to do every time. But in some circumstances, you'll see throughout these next couple days, it does make sense to keep it double blind from people. Okay, the subject nor the person interacting with them would know. Then oftentimes, you know how I mentioned control groups are also typically important? Well, sometimes when you're talking about medications, okay, that control group is actually what we call a placebo. All right, a placebo, and I'm guessing most of us have heard that term before, right? Yeah. So a placebo is just a dummy pill, okay? I think it's usually like just a sugar pill or something that doesn't actually do anything, but it gives them the idea that they're taking the same medication as everyone else. So, because sometimes just the process of taking medication, even if it does nothing, you trick yourself into feeling better, right? You think you feel better because you think you should be. You think you're taking medicine. That's what this accounts for, is seeing, are people going to react simply because they're taking a medication? Is it psychosomatic, basically? And again, this makes a really good control group, to see what if the people actually don't receive anything, how are they going to react? All right. So again, let's do an example here of maybe something that could have been done better. Fizz Laboratories, a pharmaceutical company, has developed a new drug for relieving chronic pain. 60 patients suffering from arthritis and needing pain relief are available. Each patient will be treated and asked an hour later, about what percent of pain relief did you experience? Why should Fizz not simply administer the new drug and record the patient's responses? How could the experiment be improved? So right now what they want to do is they want to give that drug to everybody and ask their pain response in what, an hour, I think it said. Why is that not a good setup? We sort of already touched on this. What's wrong with what they want to do? There's no control group. You have nothing to actually compare it to, right? You're just giving everybody this treatment and seeing how it goes. Doesn't it make sense to have a comparison, right? What else would happen? Maybe if we did nothing or something like that. So here, again, it's not authentic because you have nothing to compare it to. So here, the responses will not be useful because there's nothing to compare them with. Now here, for a control group, if you think of what would be ethical, we have a couple choices. They said this is a new drug, right? So as a control group, would we want to give them nothing? Or could we give them the old medication to compare to what's already currently out there? What would make more sense for us to do ethically? What? Yeah, so here I think the control, instead of doing nothing for them and just basically watching them suffer, wouldn't it actually be a valid comparison to compare it to the old drug, the current one out there, to see if this is maybe better than the current one out there? Because if it's not better than the current one out there, would you want to mass produce this? Probably not. All right. So to describe an experimental design using our improvement, again, what we talked about is having a control group be the current medication out there. So what we're going to do is we're going to take half of our subjects, randomly assign half of them to get the new drug, half of them to get the current one out there, and then at the end, we can compare their pain relief, right? See if maybe this new one worked better or not as well. Oh, did they actually say that there were 60 people? Oh, they did. Okay. I forgot that. So we could actually go as far as to say 30 and 30. Now, for an experiment like this, would it be possible to set up in a double blind manner? Is it possible for the patient to not know which of the medications that they're taking? Yeah, easily, right? You just make the pills look alike, right? Is it possible for the researcher interacting with them to not know which one they're taking? Yeah, someone in the background could do that for them, right? Someone in the background could already sort out which subject gets what. The person, however, that actually gives it to them wouldn't know, okay? So again, when we're talking about double blind, we're talking about somebody in the background setting it up for you, and then the person that actually interacts with the subject wouldn't know. So here, I say this is very possible to set up in a double blind manner. What? Oh, I didn't put explain. Pretend explain is there. All right. Now, I love doing examples like this because guess which year I took the AP exam? So this is one that I actually got to take when I took the AP exam back in high school. So, so uh, thanks for that. Thanks. I'm not that old. Thank you. All right. A biologist is interested in studying the effects of growth enhancing nutrients and different salinity or salt levels in water on the growth of shrimps. The biologist has ordered a large shipment of young tiger shrimps from a supply house for use in the study. The experiment is to be conducted in a laboratory where 10 tiger shrimp will be placed randomly into each of 12 similar tanks in a controlled environment. The biologist is planning on using 3 different growth enhancing nutrients, A, B, and C, and 2 different salinity levels, low and high. All right? And they want to know uh, what the treatments are. So remember, treatments, you have to be very specific as to even combinations of different pieces of your treatment. So for example, wouldn't one of the tanks be nutrient A with low salinity? And then wouldn't another one be A with high salinity? B with low? B with high? C with low? C with high. So if we're connecting those together that way, how many treatments are we actually doing? 6. Okay, so you can list them out, or I know on the AP exam, when I copied this from their rubric, they just set it up in a table. Again, it doesn't matter to me or them which you use. If you just want to list them out like we did yesterday, that is totally fine. This was just them being extra organized. All right, so now what they want to do is we have these 12 tanks. Each tank is going to have 10 shrimp in it, okay? And now we need to randomly assign each of these to tanks. Now we have 6 treatments and we have 12 tanks. What does that mean? Hmm? Yeah, so every treatment is going to go into 2 of the tanks, right? So this one we need to randomly assign into 2 tanks. This one we have to randomly assign into 2 tanks. So again, what we're talking about is going through each treatment, we need to put into 2 different tanks, okay? Now, the way that they had it structured here, right? These treatments are already numbered kind of, right? So what I would do is we have the 12 tanks. So maybe we number the tanks as well, okay? So maybe we call them tanks 1 through 12, all right? And what do we do with those numbers 1 through 12? Put it in a hat, all right? Mix well, excellent. So I mix my hat well. How many am I going to draw out first? How many do I want? I'm going to draw out 2. Those 2 that I draw, I'm going to put in treatment 1, the A low. Set them aside. Now how many will I draw? 2 more. Those 2 maybe I put in group 2, the A high. Set them aside. Isn't this just going to be a process of drawing 2 at a time until all 12 tanks have a treatment? Does that make sense? Yeah, smile, nod, give me something, guys. Yeah? All right. Bless you. So, number each tank from 1 to 12, put the numbers in a hat and mix well. Draw out 2 numbers. Those are the tanks that receive the A low treatment. Do not put those back and draw 2 more. Those are going to receive A high. Again, don't put in the back, draw two more. So basically, it's just me walking through doing that each time. Unfortunately, I know this one gets long. So again, this one, the process is easy to figure out. It just takes a little bit of time to explain what you're doing. What? Um, I mean, this was 12 years ago. I don't specifically remember what I put, but this is what I would put, like, thinking of now, what I know, this is what I would put. 5. I took calc and stat simultaneously. I got 5s on both. What? It's okay. English did not go as well for me. So, what? Yours. Wait, what? Oh.
You could actually start saying the weird flex, but okay phrase. So I feel like that's a phrase you'd like.
Okay, so what?
Weird flex, but okay. Okay, so give me an example. Be like, okay. You have what? Flex, but like flex means like if I said
Weird statement.
like if I bought a Prius and I show off that I just bought a Prius, so I'm like flexing that I just got a Prius. People are gonna
Got
be like
it.
weird flex, but okay.
Got it.
That's the biggest thing using, I guarantee. Preposterous boast, but alas.
All right. All right. Part C. So now we want to know what is a statistical advantage to only using tiger shrimp in this experiment. Okay, so here they only specifically use tiger shrimp instead of a variety of shrimp. What is an advantage to that? What? It's a constant. Isn't it easier to run this experiment? Because if we had different types of shrimp, isn't that another variable we have to account for, basically? So this one, the advantage is just that it's easier. Okay, it's convenient because we don't have that additional variable that we have to account for in setting up our experiment. All right, the final piece to this, all right, is what is a disadvantage to this? How is it limiting to us that we only use tiger shrimp? Bingo. It limits how far we can generalize our results. We'll talk a lot more about that a little bit later in the week. But yeah, it limits how well we can generalize. We can only speak about tiger shrimp instead of being able to speak about shrimp in general. Okay? So again, you could honestly summarize that a lot faster if you need to, rather than writing verbatim what's up there. So again, basically the idea is it only lets you make conclusions about tiger shrimp. You can't speak to all shrimp. So basically, again, it just limits our conclusions. Oh, good. At first, I thought that was another one. I'm like, no, I don't want 2 more pages. Close. Close. This last one's gonna go fast. Okay, so. All right, so this I'm not going to spend too much time on, all right? But one of the things we talk about is there's 3 principles of experimental design. 3 things that we want to make sure that our experiment has. First, we need to control for lurking variables, okay? So again, a control group, anything like that, we just have to control for all the things that could be happening with our experiment. We need to use random assignment, okay? If we don't, our conclusions are not going to be valid if we don't use random assignment. And then replication. We need to show that this wasn't just a one-time fluke. We need to show that this would reoccur. Okay, so just doing like one person, that's why you always see a group of people in an experiment, right? You have to show that this is a general trend. You have to show that this would be replicated if you were to perform this experiment again. Okay? So, again, let's really quickly go through. This is a real FRQ from the alternative 2006 test. So when a tractor pulls a plow through an agricultural field, the energy needed to pull that plow is called the draft. The draft is affected by environmental conditions such as soil type, terrain, and moisture. A study was conducted to determine whether a newly developed hitch would be able to reduce draft compared to the standard hitch. A hitch is used to connect the plow to the tractor. 2 large plots of land were used in this study. It is randomly determined which plot would be plowed using the standard hitch. As the tractor plowed that plot, a measurement device on the tractor automatically recorded the draft at 25 randomly selected points in the plot. After the plot was plowed, the hitch was changed from the standard one to the new one, and the process takes a substantial amount of time. Then the second plot was plowed using the new hitch. 25 measurements of the draft were also recorded at randomly selected points along this plot. All right, so a couple things. We want to know the response variable. We want to identify the treatment, and we want the experimental unit. So first of all, what are we doing this experiment on? What are the experimental units? What are we experimenting on? The hitches, all right? What's the treatment? The type of hitch used, all right? And the response, what are we measuring? The draft, all right. Oh, I'm sorry. They're saying the units were the plot of land because the hitch was the treatment. We're using the hitch on the plots of land. All right, so given that the goal of the study is to determine whether a newly developed hitch reduces draft compared to the standard one, was randomization used properly? Did they randomize here? I think it said it was randomly determined which plot would they use which hitch for. So yes, this experiment you can see they did specify that they randomly assigned a hitch to a plot. Now, on the flip side of that, the next part is did they use replication properly in this study? Did they replicate this effect of the hitches? How many plots of land did they use each hitch on? They only used it on one plot of land. Is that showing replication? To only use it on one plot of land? So yes, they took measurements within each plot. They took multiple measurements, but in terms of the plots themselves, they only used one hitch on one plot. So that isn't showing that this is a general trend for if they used it on other plots of land. All right, and part D. So this is what I meant um when they ask about confounding, oftentimes they'll kind of guide you in the direction they want you to go. So in this one, they specifically tell you, hey, the plot of land is a confounding variable. And they want us to explain what that means. So again, confounding means that the plot of land is going to be indistinguishable from the effect of the hitch. Why would that be? Why would the plot of land, why would you not be able to tell is the effect on the draft from the plot of land or the hitch? Why is it confounding in this case? There's a very specific reason for it here. What? Yeah, and specifically, didn't we only use each one on one plot of land? So that's why, yeah. These plots of lands, they said in the prompt, soil, this, that, I forget what the other things were, can have an effect on the draft, right? So you only use each hitch on one plot of land. So maybe it's the land that is altering the draft, not the hitch that was used. You don't know because you only did each one once, okay? So that replication this time is kind of what created this confounding.